All right, so as I warned, the semester will go by fast. First test is next week. If I don't do so, remind me to tell you by the end of class what the written question will be. And same for the next time. If I forget before, just remind me. Tomorrow at in room N2201, there will be test review. So if you have time before then, so that'll be at 1 p.m. for 1100. If you have time before then, go through the key terms, see if there's anything that's still unclear, and you can either ask about it on course questions or come to the in-person test review. Also, a general piece of advice I've given to all my classes, on multiple choice, some students think that the number of answers for each letter has to be equal, and so they develop formulae for making sure they're equal. I encourage you to not waste your time doing that. Just focus on what the best answer is. So unfortunately, I'm feeling a bit under the weather, and as you've all probably already discovered, I can be a bit, unhinged. I kind of just teach extemporaneously, so hopefully I keep it more or less on the rails today. Luckily, I suppose, today's topic is pretty boring. We're doing chapter 2, which is on research methods and a bit of statistics. So this is very important. It's the only chapter that's covered both in 1200 and 1100, so it's the 4th time I've taught on it this semester, so but very important to understand. So we're going to start with a little task. I want you all to write down, on a piece of paper or on the computer, 2 numbers. I won't be asking for these numbers, it's just to get you thinking. Those 2 numbers are how many sports you played in high school and how extroverted you are on a scale of 1 to 7. So 7 being very extroverted, meaning outgoing, socially confident, etc. So as I say, I won't ask for this, but if I wanted to, I could collect your data and represent your scores on something called a scatter plot. So normally I go through the chapter in order, but this set of concepts I'm starting with are, I think, the most important in the chapter. So for this little bit, I'll make an exception and go out of order. So let's say we put sports on the x-axis. Let's say it ranges from 0 to 5. And we could then put the other variable, the extroversion, on the y-axis. And as I said, I wanted you to answer from 1 to 7. So we could locate people in this 2-dimensional space. So let's say someone played 5 sports in high school and their extroversion score is 7. They would be right there. That's their that's their location in this 2-dimensional space. So then we can put a bunch of people in here. So this would be an example of a correlation. A correlation is where 2 variables vary together or change together. In this case, this would be a positive correlation. A positive correlation is a correlation wherein as one variable increases, the other variable increases as well. The way the book says this is more is more. More of one means more of the other. And in this course, we will limit ourselves to linear correlations, meaning correlations that are best approximated by a straight line. So you can have examples where the correlation is curvilinear or exponential, where some kind of curved line is a better, or curved function is a better approximation of the relationship. But as I say, in this case, for intro, we'll stick to linear relationships. So So this one is positive. A negative relationship would look like this. So maybe the correlation between video game usage and GPA. I don't know if that's true, but it's plausible. So a negative correlation means that as one variable increases, the other decreases. As the book says, more is less. So let's focus on this correlation then. It's very tempting to look at a relationship like this and make the following inference. It's very tempting to go, people who play more sports are on average more extroverted. That must mean that playing sports leads to more extroversion or causes more extroversion. My son, Timmy, is very shy. I should get him to play sports, and then as a result, he'll be more extroverted. So I see some cringes. The cringes are good. That's a mistake. This is probably the most important thing that you can learn in a psychology course. It applies to the other sciences as well. And that thing you should know is correlation does not imply causation. You should tattoo that to your forehead. Correlation does not imply causation. How many of you have heard that before in other classes? Maybe half. So the reason is, whenever A and B are correlated, there are three possibilities. One is that A causes B. So that is possible. It's one explanation of these data. Nothing wrong with it. It's just that you can't go straight from this to this. It's only one of the possibilities. So it could be that playing sports causes more extroversion. It could also be that B causes A. So in this case, it could be that being more extroverted causes you to play more sports, right? Maybe people who like people more, that makes them think, I'm going to join more sports teams so I can interact with more people. Perfectly plausible. And finally, it could be that C, some unknown variable that you didn't measure, causes both A and B. So C could be anything you didn't measure. I'm just making this up, but maybe the third variable is income. Maybe people who have more money are more extroverted, they're more confident or arrogant, and as a result more extroverted, and they play more sports. You know, their parents got them into more sports when they were young because they had more to spare. As a result, they play more sports. Now, as I say, I just made that up. C could be anything. It could be height, income. You can make up other possibilities. And the crucial point is you don't know which of these is true just based on this. Any questions about that? Now, we want to know about cause and effect relationships, so this is a real shame because for two reasons. One, it's just scientifically interesting. We want to know about what causes what. But it's also important for interventions. Oftentimes we do scientific research in a given area because we want to know how we can help people, how we can intervene to make a difference. For example, we may in some cases want to teach people to be more extroverted or more outgoing, and in order to do that, you have to know about cause and effect. So, if we want to know about cause and effect relationships, we have to do an experiment. So here's the basic setup of an experiment in psychology. We'll see more detail later when we return to this in the middle of the chapter, but I'll give you the kind of zoomed out version. So in general, like across the sciences, what an experiment is, it's a study where you control all variables and manipulate one and see what happens. The way that we hold variables constant in psychology is random assignment. That's the key ingredient of an experiment. So we get a group and randomly assign people to multiple conditions. The reason that random assignment is so crucial, so this would be like, for each person you flip a coin. Okay, heads, you're in condition 1. Tails, you're in condition 2, and so on. This is supposed to make it so these two groups are roughly the same for all variables. If you have a big enough sample, there should be roughly the same number of happy people, extroverted people, people who love video games, whatever, in each condition. And then you manipulate a variable. So in this case, let's say this group plays 5 sports for 6 months, and this group plays 0 sports for 6 months. And then after that, you measure their level of extroversion in each group. Now, I doubt the difference would be this big, but let's suppose that at the end of that, this group, the average is 5.5 out of 7, and in this group, it's 2.6 out of 7. So now, you have good evidence that playing sports causes extroversion because of the key step of random assignment. These groups should be roughly the same level of extroversion at the beginning. You manipulate sports. As a result, this group is more extroverted. 2 other key terms. The variable that you manipulate or control, does anyone know the fancy term for that from another class? So the term for the variable that you manipulate or control is the independent variable. Sometimes called the manipulated variable. The variable that you measure at the end is the dependent variable. So in this case, extroversion. If you want a way to remember that, think about what your hypothesis is. So in this case, your hypothesis that you're testing is sports causes more extroversion. If your hypothesis is right, this variable depends on this variable. That's what it means to be an effect of something else, right? It's dependent on it. So the dependent variable, if your hypothesis is right, depends on the independent variable. So it's easy to mix them up, but hopefully that helps. As I say, I'll add more details later, but any questions on the basic logic of an experiment? Okay, so now we'll start going through the chapter in order. The first term in the chapter is one we've already talked about, which is empiricism. So you'll recall that last time I made a distinction between 2 different senses of the term empiricism. In the context of chapter 2, we're only concerned with the justification sense. So in chapter 2, the issue is how do we know whether something is true? How do we know which of our ideas are right? And the answer that an empiricist gives is you have to rely on observation. You can't just sit down and think about something. You have to go and test it in some way. So do a measurement, an experiment, something that involves looking with your 5 senses. The book then talks about the distinction between a theory and a hypothesis. This is probably a review, but I'll try to make it clear if you've forgotten. So a theory you can think of as sort of a network of hypotheses. It's a set of ideas that are logically related that explain a large body of data. So think about Darwinian theory. Darwinian theory is not one sentence, right? It's a set of ideas that are related to each other that explain a large body of data. A hypothesis is a specific testable statement. Typically, though not always, a hypothesis will follow from a theory in some way. So, if the theory you're working with is Darwinian evolution, you may compute that you should observe a certain type of fossil in a certain layer of rock. So, the sentence that I should find this type of fossil in this layer of rock, that's a kind of hypothesis, specific testable statement. We talked last class about falsifiability. One key point that the textbook makes at this point is that you can't prove a theory right. This is an important point that philosophers of science make. You can find evidence that's inconsistent with a theory, and that proves it wrong. But finding evidence that's consistent with a theory doesn't prove it right, because future observation may show it to be wrong. So one example is Newton's theory, which you don't need to know, but Newton's theory was supported by virtually all of the relevant observations for hundreds of years. But that didn't mean that it was proven to be right, because eventually Einstein's theory superseded it. There were certain things, for example, Mercury's orbit, that Newton's theory couldn't explain, but Einstein's could. So what we're trying to do is disprove theories, and if we fail to disprove a theory, we don't say we know that it's right, just that it survived our attempts to prove it wrong for now. Okay, so that's a very important ideal in science. Another ideal in science is precision. We want to be as precise as we can. This is difficult in psychology because many of the variables that we are interested in are difficult to define. So things like intelligence, happiness, anxiety, it's controversial how to define these. So what's the solution? The solution we've opted for in psychology is giving operational definitions. So, to give an operational definition is to define a variable in terms of the operations used to measure it. So, put more loosely, it's giving a precise, measurable definition of something. So here's a standard example that's given in textbooks. Take intelligence. We talk more about this in 1200. So there's debate in psychology about how to define intelligence, but when you do an experiment or some other kind of study and you write it up for a journal, you won't include a long philosophical section about, what's the nature of intelligence? Typically what you'll do is you'll operationalize it. And the standard way of operationally defining intelligence is IQ score. So that's something that's precise and measurable. Now, we know that IQ tests are not without flaws, but it's a way of making it, as I say, measurable. In fact, just at the beginning of class, we operationally defined a variable. When I asked you all to write down your own extroversion score on a scale of 1 to 7, that's a way of operationally defining extroversion. Right? There are some scales that will be longer, but that's a simple way of making it measurable. Now, not all operational definitions are created equal. There are two key features we want operational definitions to have. Reliability and validity. Now, the word validity is used in different senses in psychology. In this context, we mean construct validity. This is validity in the context of measurement. So I'll start with reliability. Reliability is about how consistent the results you get from a measurement are. Put another way, does the test or the scale allow for consistent results? So if I make a new IQ test, I give it to someone on Monday and they get a score of 87, give it to them on Friday and they get a score of 84. By the standards of psychology, that's pretty reliable, right? Pretty consistent. If I give it to them on Monday and they get 142, give it to them on Friday and they get 61, okay, that's bad. Right? It's not very reliable. So what about validity? Well, here's an example that shows why reliability is not enough. I'm modifying this from another textbook. Suppose that I want to become famous and I invent the following new IQ test. To get your IQ score, I measure the length of your left pinky toe. And I say, that's your IQ score. When you think about it, it would be a very reliable test, right? Unless you have an unfortunate accident, same IQ score every time you do the measurement. What it would lack is validity. Validity is the test measuring what it purports to measure? So in this case, the IQ test purports to measure intelligence. My silly pinky toe example, clearly not valid. So this latter concept is more contentious. There are different ways of getting at validity. I'll give you one example that you don't need to know for the test, but it'll just help you see what's going on here. One way of getting at it is criterion validity. Criterion validity is the test correlated with something that it should be correlated with? So one thing that's been done in the context of IQ scores is you can look for correlations between IQ scores and grades. If there's zero or close to zero correlation between IQ scores and grades, it seems strange to say that these are measuring intelligence. Now, the correlations, of course, in psychology are never perfect, but that would be one way of providing evidence for validity in the context of measurement. Any questions about those two concepts? Okay, so there are different problems we can run into when doing these kinds of studies or tests. One is demand characteristics. So you bring people into the lab, you give them whatever scales you give them, and what participants may sometimes do is guess at what they think the hypothesis is and try to help you out. But in fact, we don't want that. We want people behaving kind of authentically as they would in the real world, but demand characteristics is when something about the lab setup leads them to think, oh, this is what they're looking at, and then behave differently as a result. So that's bad, we don't want that. Another bad thing participants can do is engage in social desirability bias. This is a big problem for self-report. Often, when we want to know about someone's psychological states or traits, we just ask them. We want to know how happy someone is. We just ask them, how happy are you on a scale of 1 to 7? Self-report. As you all presumably already know, sometimes people lie. As it turns out, people are not always honest. This is one particular kind of lying or bending of the truth, wherein people try to respond in a way that makes them socially desirable. Basically, trying to make yourself look good. So there's different ways of addressing this. One that more studies should do, actually, but it's included in a scale called the MMPI, is you can give sort of lie scales that are picking up on this, where you include a random set of items throughout the study or throughout the scale, where the socially desirable answer is true of almost no one. So, have you ever done anything that you're ashamed of? No, never. Have you ever missed a day of flossing in your life? No, never. Okay, maybe you're very special, but if you give the socially desirable answer to all of them, probably you're just bending your answers, and we may discard your data. There are other ways of dealing with this. Another thing is to look at not just self-report, but things like physiological measures, like look at their brain activity or their heart rate. These are, harder to bend bend intentionally, or overt behavior. So that's another way around that. Because in addition to, and this isn't a key term, but in addition to social desirability, people may sometimes not have good insight into their own psychological states. People may be unaware of what their states are. So that's another problem with self-report. So I mentioned measuring behavior. One way of measuring behavior that's maybe even less susceptible to social desirability bias is to do naturalistic observation. This means observing people in their natural habitat, if you like. So not bringing them into the artificial setting of the lab, watching them in the real world. So you have to kind of be unobtrusive, like sit off to the side, take notes, and try to pick up on patterns. You may be interested in patterns in bullying behavior. So you go to a school, sit and take notes. You should do so with permission from the school, of course. It's probably a good call. By itself, you probably would not get a study like that published. It's a good way to, as I say, find patterns, generate ideas, but you're not experimentally manipulating anything. You don't have the control that you do in the lab, so probably you want to replicate those patterns in a more controlled setting. So those are some problems related to participants' behavior. The next problem relates to the behavior of the experimenter. This is given, there's different labels for this in different books. This book calls it observer bias. As I say, this relates to the behavior of the experimenter. So let's suppose that I invent a new antidepressant. And I do an experiment, so I get a group and I randomly assign them to two conditions. One condition gets the antidepressant, one gets the placebo. Placebo being just like a sugar pill to just give people the sense that they're going to do better. Now, if I know who's in which condition, this is a problem. So let's say like these two are both in the study, you get the antidepressant, you get the placebo. If I know who's getting which drug, I may, not deliberately, I'm not a fraud, I'm a good scientist, but I know deep down I want my drug to work, so I may express more optimism when handing the drug to you. When I give you the piece of garbage, placebo, I may subtly communicate that I'm not so optimistic. So then at the end of the study, you're very happy and you're very depressed. And I conclude the antidepressant works. Of course, it may not be because the antidepressant works, it may be because of my behavior. Does anyone know the term for the solution to this? There's a type of study. Yep.
Double-blind study.
Double-blind study. So a double-blind study is one in which the participants don't know who's in which condition, and I, the experimenter, don't know who's in which condition. As an aside, a single blind means just they don't know. But if you can do double blind, that's better. Obviously, some lab rat in the back knows who's in which condition, but no one interacting with the participants knows. Okay. Next, we have to talk about how we select people to be in the study. So, two groups that we can talk about. There's the population, and this is the set of people that we are interested in. So, this could be all humans. Going to make it hard to get a representative sample if that's your population. It could be all Canadians, all Douglas College students. You can define it however you want. But typically, if the population isn't all interesting, it's going to be hard to study every single member, so we get a sample. What we want is this sample to be representative. Representative means similar to the population in terms of demographics. So if the population is 50% male, the sample should be 50% male. If the sample is 10% East Asian, so if the population is 10% East Asian, the sample should be roughly that as well. There are different ways of making the sample representative. One is to use random sampling. So you get a phone book or whatever, like a list of everyone in your population, get a random number generator, and use it to pick who's in the study. If you do that, and the sample is large enough, it should be roughly representative. Warning. Do not confuse this with random assignment, which we talked about earlier. Random assignment is about once you've already got your sample, you already got your people into the lab, and you randomly assign them to two or more conditions. Whereas random sampling is about getting people to be in your study in the first place. So make sure you don't mix those up. Random sampling is one method of making the sample representative. A simpler way is to use stratified sampling. If you use stratified sampling, you force the sample to be representative. You can stratify by as many variables as you like, and what you'll do is set cutoffs for different demographic groups. So, I helped run a study in Georgia State when I was doing my master's there. We stratified by age and gender. So we wanted, I think it was 600 people, and once we had whatever it was, 80 males, 40 to 50, okay, no more males 40 to 50, and so on for the other ranges. So when you do that, you force it to be roughly in proportion to the population. Any questions on sampling methods? So once you have your sample and you've collected your data, there are different ways of summarizing the data. One important method, or kind of graphic representation, is a frequency distribution. So with a frequency distribution, on the x-axis you have different scores. So let's say you're looking at height, ranging from 410 up to 6'5", let's say. And then the bars here would correspond to how many people are at that score or level. And what you find for many traits in psychology and actually in other sciences too, is that they look something like this. That's not very well drawn, but where most of the scores are close to the middle, and they become increasingly rare as you go out to the tails. This is sometimes summarized like this. You can run a curve through it, and this is usually a pretty good approximation. Does anyone know the term for a distribution like this?
Normal distribution?
Yeah, normal distribution or bell curve. The chapter launches a personal attack and says if you'd like to remain single for the rest of your life, you can add that you know it's also called a Gaussian distribution. Ruthless textbook. So that's how a lot of traits follow. So when we look at distributions, there's two things we care about: central tendency and variability. We'll spend some time talking about each of these. Central tendency is about where the middle of the distribution is. Where do the scores tend to fall? By far the most commonly used measure of central tendency is the mean. This is the same as the average. So I'm sure you all have calculated an average at some point in your life. You add up the scores, divide it by the number of scores. So that's all this is. As I say, by far the most common, but there's a key weakness that the mean has. Let's say I'm working for an aid agency. I'm looking at different villages and looking at how rich or poor they are. And I come across a small village with 5 people. 4 people have literally $0, 0 monies. And a 5th person has $1 million. Anyone who's good at math in their head, what's the mean net worth in this village? Nope. So it's $200,000. So you just add it up. So 0 plus 0, 4, obviously 0. $1 million divided by 5, 200,000. So now I go to my boss and I say, you know what? This village, they don't need any help. They're pretty good, 200,000 average. Now, I haven't lied. That's true. But you should all see that that's pretty misleading, right? This village is pretty poor. There's just one lucky dude. So this is the key weakness of the mean, is that it is sensitive to outliers or extreme values. If there are values that are high above the mean or far below the mean, they can affect, or I should say high above the other scores, they can significantly affect where the mean falls. So this example should make that clear. So in a case like that, you typically will see the median reported. The median is the middle score. So you take the scores, rank them from smallest to highest, and then just pick the one in the middle. If there's 2 in the middle, like if it's an even number of scores, then you just take the average of those 2. So whatever score or 2 scores fall in the middle, that's the median. So for example, if you go home and Google average income in Canada, it will be very hard to find the mean. What will typically come up first is the median, because there's a few billionaires, they drag the mean up higher than it sort of should be. Or at least it's not, it's misleading to report the mean. And then the last one is the mode. The mode is the most commonly occurring score. So let's say you have, there's another village, guy has $1, another has $2, another has $4, and then 2 guys have $8. So the median in this case would be 4, it's the middle score, and 8 would be the mode. It occurs 2 times. Theoretically, you can have situations where a distribution has 2 modes. These are called bimodal distributions. Sometimes you get something like this. I was once in a logic class where the prof, I don't know why he told us this, but he told us that the grades looked like this, that people either totally got it and were in the 90s, or they didn't get it at all and were like failing or almost failing. Hopefully it doesn't happen to this class, but you can get that sometimes. Okay, any questions about central tendency? So, nothing too fancy in the statistics section in chapter 2. So the other thing we care about is variability. So variability and central tendency come apart. You can have cases where 2 distributions have the same mean, but different amounts of variability. One controversial example that there's some evidence for is IQ. So the average income for males and females is 100, same average. But some studies find that the male distribution has more variability, meaning more spread. So more at the very high and very low end. So some studies fail to find it, but that would be an example of variability and central tendency coming apart. So how do we measure central tendency? Or sorry, how do we measure variability? So the easiest method is to use the range. It doesn't give you as much information, but the range is just the largest score then minus the lowest score. So let's suppose in this class, one person gets 100, best mark in the class, and one person gets 1%. The range is 99, dead simple. So that's the range. By far the most commonly used measure of variability is the standard deviation. How many of you have heard the term standard deviation? Maybe half. So I'm going to explain the standard deviation in 2 ways. First, I'm going to give you a definition that's not quite right, but it's good enough for this class. This one is good enough, for example, to do well on the test. In addition, I will show you how to calculate it. This may help you in future classes, but if the thought of looking at Excel and math scares you, you can turn your brain off for like 2.5 minutes. So I'll start with the definition that's a good first pass, although it's not quite right. The standard deviation is roughly how far away on average are scores from the mean. So you have the mean, you have the average. Some scores are very far away, some are very close. Okay, how far away on average are they from the mean? So now, in addition to that, I'll show you how to calculate it. So here I have a hypothetical list of grades, ranked from lowest to highest. So the first thing we do is calculate the average. So that's the average grade in this course, 77.1. Okay, now what I'll do is I'll take each score and subtract the mean. So this is the deviation. So that should look right? That person, Bob, is 17.1 points below the mean. So that's his deviation. Then I do the same thing for everyone. So this is how far away each score is from the mean. So some are close and some are far. Now, you might think, well, why don't we just add these up and do that? So let's try some. Let's try adding them up first. That's 0. And when you think about it, that has to be right. Because how far away are they from the mean on average? Well, on average, they are the mean. So the negative and positive cancel out. So what we have to do is make them all positive. All of the deviations positive, so they're in one direction. There's different ways of doing this. When we're doing the standard deviation, we square them. So we raise each one to the power of 2. So we're multiplying each one by itself, and when you multiply a negative by a negative, it's a positive. So that's the squared deviations. And then we just get the average of that. Now, that's way too big, because when we square something, we make them all positive, but we also make them bigger. So the final step is square root that. So we get it back down to a good size. So square root this, voila. That's it. That's the standard deviation. So take all the deviations, so how far away each one is from the mean, square those to make them positive, average it, and then square root it to make it smaller again. And this number should look right? So a little over 10. You look at these, yeah, some of them are close, some of them are far, but that's a good, yes?
So what we're doing is we're finding the average of the absolute value of the deviations?
No, so technically the average of the absolute deviations, you can do that. That's a different measure. It will typically be similar to the standard deviation, but technically that's a different measure. Don't worry about that if you didn't understand what I said. And in fact, as I say, if this Excel thing gives you a headache, you can just stick to the conceptual definition and repress your memory of this until you take Site 2300, when it will come back. Any questions on the standard deviation? Someone should fix that. There's something I forgot to talk about that relates to some extent to both, but it more relates to central tendency. And that's different types of skew. So when I was talking about the mean, I talked about outliers, how extreme values can significantly affect the mean. So there's two kinds of distributions you need to know. So here, the long tail at the end would correspond to outliers, right? A few values that are way out here. This would be an example of a positively skewed distribution. So there's two ways to remember this. One is think about where the skinny tail at the end is. Another way is to think, which way will the mean be dragged? So it looks like the mean should be here, sort of, but in fact it'll be somewhere like here, because the extreme values will drag it in the positive direction. So that's an example of positive skew. And then, negative skew would look something like this. where there's a few outliers way out here, and then the mean will be dragged somewhere like there. So important to be able to distinguish those. This is one case where the mode is interesting to know, right? The mode will be here, right? It'll be the peak of the distribution, because that's where the most commonly occurring score will be. Okay, so next we get back into correlation and experiments, this time with more detail, but that's a natural place for a break. So let's take a little less than 15. Let's come back at 4:35. Okay, everyone, get back into it. So I started the class off by talking about correlational studies and experimental studies. So now we've arrived at the part in the book where it goes into this in more detail. So I started off by talking about negative versus positive correlations, with the caveat that, again, we're only talking about linear ones that are relationships that are best approximated by a straight line. So correlations can also vary in terms of how strong they are. When we quantify it, it goes from +1 to -1. The further away from 0 the correlation is, the stronger it is. So +1 and -1 are both they're as strong of a correlation as you can have. This is what a correlation of +1 would look like. And this is what a correlation of -1 would look like. In the real world, particularly in psychology, you will never see this. Often in psychology, if we get 0.3, we're like, that's pretty good. We're pretty happy with that. Because things are very complex in psychology. So what these mean is, if you know someone's score on one variable, you can predict with 100% confidence their score in the other variable. I mean, you can cheat and get something like this. So, you could do someone's height in inches and their height in centimeters. Like, well, yes, perfectly positively correlated. I wouldn't recommend trying to get it published, but that would be a correlation of +1. So then from there, a correlation of positive, let's say 0.8 would look something like this. So, pretty strong. They're pretty tightly clustered around that line, but there's a bit more randomness, a bit more spread. Now, this isn't exact, but correlation of +0.3, maybe something like this. Right, there's like a general trend in one direction, but now there's quite a bit of noise. And this may not be visible in the video, but you can Google correlation of 0 if you're watching the video. Correlation of 0 would be a flat line, and the dots are all over the place, no trend. So I use that pinky toe example. Probably, I haven't done the study, but the correlation between pinky toe length and IQ, probably 0 or at least close to 0. Right? If you know someone's score on this variable, you have thereby gained no information about their score on the other variable. And then the same idea here, just the mirror image. So negative 0.8, something like this. Positive 0.3, something like that. Now, so you should understand this. You should know that a correlation is, if it's further away from 0 in either direction, that means it's a stronger relationship. So you should be able to distinguish the direction of a correlation from the strength of a correlation. Does that distinction make sense? Any questions about that? So I forget if there's one in this class, but there may, for example, be a question on the test where you have to look at different scatter plots and identify which is positive or negative and which is stronger or weaker. If there is such a question, it will not be a close call, as long as you get this general point that, when it's a strong relationship, they're tightly clustered around the line, and the number is, as a result, further away from 0. So given that we can't infer causation from correlation, what are correlations good for? One thing they're good for is making predictions. So here's a couple of examples. One thing that universities and colleges do is they look at high school GPA. And what they're doing is using it to make a prediction about what your college GPA is likely to be. And they're not doing this for no reason. There is a positive correlation, right, between the two, even though there will be some exceptions. Maybe some of you will be exceptions, right? Maybe some of you, low high school GPA, but you may decide to start studying harder and kind of break the trend, so to speak, or go against the trend. And sadly, some of you may be the opposite kind of exception, where maybe you did well in high school, but start partying more or start abusing substances that you shouldn't or whatever. But the general trend is there, and this is what allows us to make predictions. It's also used a lot in the justice system. So one psychological scale that's used, actually a professor here in the department, Brian Nadeau, used to administer this. It's a measure of psychopathy, so how psychopathic you are. It's called the Psychopathy Checklist Revised. It is correlated with your likelihood of recommitting crimes once you leave prison. So it's useful to know what someone's score is, because you can make a guess about how likely they are to commit a crime once they're released. That's another example. As I said, though, if we want to know about cause and effect, we have to do experiments. So I gave my own example, but to reinforce it, I'll show a video of Hank Green. Crash Course Psychology is a great resource. Okay, so well said. I'm going to build on this in a few ways. One, I'll just mention two terms that he mentioned in passing that I didn't talk about, experimental group and control group. So the experimental group will get more of or high dose of the independent variable, and the control group will get less of or none of the independent variable. So in this case, decaf versus more caffeine. Now, there are actually many different types of experiments in psychology, different ways of classifying them. One important way is the distinction between a between subjects, or I should say, the emphasis on between subjects experiment and a within subjects experiment. Between subjects is the standard case. And if you're given no information, you should assume it's probably a between subjects experiment. Everything we've talked about so far would fall under the heading of between subjects. This is where you get a group, randomly assign them to two or more groups, and do something to one group that you don't do to the other group. And at the end, this is where between comes from, you're looking for a difference between the two groups of subjects. Hence, between subjects. In a within subjects experiment, there aren't multiple groups. There's one group, and they get exposed to both or more versions of the independent variable. And you look for differences within each subject. If that sounds abstract, we'll actually do a within subjects experiment right now. So it's a little memory task. here's how it's going to work. And you will not have to reveal what your score was, but I am going to read you a series of word pairs. And here's version 1 of the, or level 1 of the independent variable. I'm going to ask that you say these word pairs in your head. So kind of audibly go, for example, if the word pair was jar hammer, just in your head go jar hammer. Okay? So straightforward enough. I'll now read the word pairs. Zebra, jeans. Banana, moon. Chocolate, textbook. Toe, ketchup. Insect, scientist. Thermometer, knife. Box, chair. Can, pepper. Okay, so now that was 8 word pairs. I'm going to say the first of each of the word pairs, and if you remember, write down the second one. So you can write down 1 through 8, and we'll see how we all do. So number 1, zebra. So write down the other one if you remember it. Number 2, banana. You guys remember that video, I'm a Banana? It's great. If I've never been high, but I think if I was high, it'd be pretty good for anyways. Okay, next word, number 3, chocolate. Number 4, toe. Toe. Number 5, insect. 6, thermometer. 7, box. And 8, can. Okay, so now we'll go through the right answers and you can add them up and figure out how many you got right. So number 1, the right answer was jeans. Number 2, moon. 3, textbook. 4, ketchup. 5, scientist. 6, knife. 7, chair. And 8, pepper. I'm seeing looks of great confidence. Okay, so next level of the independent variable, same idea. This time, don't audibly say it. Instead, form a visual mental image of the two things. So for example, if it was jar hammer, form a visual mental image of, a jar with a hammer in it, or some other way of putting the two together. Make sense? Okay. Cow, shoe. Dog, dress. Apple, toilet. Boat, tree. Table, baby. House, backpack. Fridge, coat. Microwave, grape. Okay, so same idea, 1 through 8. I'll read the first word. Number 1, cow. Number 2, dog. Number 3, apple. Number 4, boat. 5, table. 6, house. 7, fridge. And 8, microwave. Okay, we'll go through the right answers again, and you can tally up how many you got. Number 1, shoe. Number 2, dress. Number 3, toilet. 4, tree. 5 baby, 6 backpack, 7 coat, and 8 grape. Okay, add up how many you got right, and now look at which condition you did better in. So show of hands, who did better in the first condition? So one person. Who did better in the second condition? So yeah, that's pretty typical. Usually there's a handful in the first, but every time I've done this, way more do better in the second one. So this is an example of a within subjects experiment. There's not 2 groups, you all just did both levels of the independent variable. By the way, what is the independent variable in this case? The independent variable. So another way of saying it, what's the variable I manipulated?
Oh, dependent variable. The thing that you manipulate.
So independent is the one I manipulate, dependent is the one that's measured at the end. So what's the independent variable? What's a way of saying it? So maybe it's too late in the day, but it would be something like memorization strategy, right? Audibly saying versus visualizing. That's the thing that I think is going to have an effect on something. The dependent variable is how many words you got right? Your memorization score. Remember, if my hypothesis is right, the independent variable causes a change in the dependent variable. So that's a within subject experiment, but there's a problem with the way I did this. Can anyone tell me what the key problem is? Yep.
It's because when we did the second one, we already had a round.
You've already, exactly. So I will say as an aside, if you do this experiment properly, you still get the same effect. But in this case, when you do the visualization strategy, you've already had a chance to do it. So you may have done better because of visualization, or you may have done better because of practice. You know, sometimes usually a few people do better on the first time. Maybe they do worse the second time because they're sick of it. You know, they're kind of bored of this activity. So the point is you don't know. So if you want to do a within subject experiment properly, you're supposed to do what's called counterbalancing, which is where you control for order effects. So if I was doing this properly, some of you would have done it in the reverse order, right? You would have done visualizing first and auditory second. Okay. Any question about the distinction between those 2 types of experiments? Okay. Next, we'll talk about 2 types of validity. It's a shame they use the same word, because earlier we talked about validity in the context of measurement, which is about, is a test measuring what it's supposed to measure? In this context, the 2 types of validity have to do with, basically, did you set up your experiment properly? The first type is internal validity. And it's called internal because it's about within the context of your experiment. We're not worrying about the real world outside of the lab, just within your study does it have this kind of validity. This is about how confident you can be that the independent variable caused a change in the dependent variable. Again, within the context of your study. So the independent variable could be, real drug versus placebo. The dependent variable could be depression. People in the drug condition have lower depression scores. Okay, how confident can you be that it was the drug that led to a change in depression scores? Or in the study we just did, there's a problem with internal validity. Internal validity in that context would be, how confident can I be that memorization strategy caused a change in memorization scores? Yes?
Is this one related to the p-value?
You can connect to the p-value. I wouldn't worry about connecting it there. So I'll talk about the p-value later in the context of replication. So I would hold off on the p-value, but it's a good question. So that's this. Now, the main threat to this kind of validity is confounding variables, which I'll talk about here. So here's an example. Let's say I'm interested in two teaching methods, A versus B. So this is my independent variable, teaching method. So I try out teaching method A on a class in Edmonton. So as you know, I used to work at the University of Alberta. And I try out teaching method B in Vancouver. So this is the IV. And then the dependent variable would be grades. So let's say people who got teaching method A have an average score of 87, and people in teaching method B have an average score of 55. And I conclude teaching method A is better than B. It caused the kids to get better grades. What's wrong with that inference? What's another possible explanation?
Demographic or socioeconomic status?
Yeah, exactly. What or why? What's the reason to suspect there's a difference there?
So demographics in terms of cities, like difference in socioeconomic status.
Between the two cities.
Between the two cities.
Exactly.
A variable, like a third-party variable, in between like the difference in grades.
Exactly. So, one group is from Edmonton, one group is Vancouver. There could be any number of differences between Edmonton kids and Vancouver kids. Could be socioeconomic status. Could be that Edmonton kids are smarter. It could be that Vancouver kids are just very sad because they never see the sun and they can't bring themselves to study as a result. Any number of things. So in this case, city is an example of a city they're from is an example of a confounding variable. In the context of an experiment, a confounding variable is anything that's different between the two groups other than the independent variable. You want it to be the case that the only difference between the two groups is the thing that you manipulate, the independent variable. If anything else is different, to start off with, between the two groups, then you don't know if this is due to the independent variable or the confounding variable. So that's the main threat to internal validity. Any questions about that? Okay. The other type of validity is external validity. So here, we want to know, will the pattern that we found generalize to the real world? So we got our sample into the lab. We did whatever we did. But here's the thing, as I always say to my classes, no one cares about the 100 people you brought into the lab. Those people don't matter. You want to know if this is a pattern that will be replicable, that will, or I shouldn't say replicable, I should just say a pattern that will hold in the real world. Here there are different threats, but there's two in particular I want you to know. One we've already touched on, and that's an unrepresentative sample. Right? If your sample is all white dudes from Vancouver Island, you may find a pattern, but you can't have any confidence that will generalize beyond white dudes from Vancouver Island. Right? So that's one threat. Another threat has a fancier name, but I'll just keep it simple. I'm going to call it unrealistic lab situation. So as an example, I always use my own work as an example. I won't pick on other people, I'll pick on myself. So in grad school, my main area of research was moral psychology. So I looked at how people respond to different sorts of moral dilemmas and moral questions. But when you look at what I'm actually doing, I'm getting people to respond to questions on a computer, that, describe some scenario and ask how they would respond. Now, in the real world, moral dilemmas rarely present themselves in that way, right? If in real, human interaction, and it may be that how they respond in that kind of contrived lab situation may not correspond to how they would actually respond to a moral dilemma. So that would be a potential threat to the external validity of those kinds of studies. Any questions about those two threats? Okay, one method that could potentially have problems here, but it is commonly used, is a case study. So case studies involve looking at a small number of people, or sometimes even one person, in depth. Typically we do this if the people or person has some kind of special condition that makes them theoretically interesting in some way. One area where this is commonly used is neuroscience. And I'll say a little bit about why. So most of the research in human neuroscience is of necessity correlational. We look at correlations between activity in different parts of the brain and different psychological responses. You stick someone's head in an fMRI machine, you get them to solve a math problem, you look at which parts of the brain are more active. It's the parietal lobe. Okay, so parietal lobe activation is correlated with solving math problems. But as we've already seen, correlation isn't causation, so you're limited in the kinds of inferences you can make from that kind of data. With animals, as we'll see towards the end of the chapter, we are more loose with the ethics. So with animals, you can destroy different parts of their brain and look at what they can't do anymore. Some ethicists object to this, but for now, that's kind of the standard. So you can learn a lot more about cause and effect relationships in the context of animal neuroscience, because you can actually manipulate which parts of the brain are intact or not. So we can't do that with humans. So sad. Very sad for the neuroscientists. But we take advantage of the fact that people are dumb. People do foolish things and hurt their brains all on their own without the neuroscientists' help. So come into the lab. With consent, of course, we can then perform different psychological tests. If this particular part of the brain was destroyed via an accident or a tumor or what have you, we can then make inferences about what kinds of functions that part of the brain was involved in. So that's an example where a case study is very useful. So we'll be seeing cases of this in chapter 3, which is after the test. Probably the most famous case is Henry Molaison. Maybe Phineas Gage is a bit more famous, but Henry Molaison had life-threatening seizures emanating from his hippocampus. His entire hippocampus was removed by a neurosurgeon, and he lost the ability to form new long-term memories. So, plausible inference that the hippocampus is involved in generating new long-term memories. So that's an example of a case study. Okay, so someone mentioned the p-value. I'm now going to build up to that. It's a very important concept to understand. So the p-value I'm going to bring up in the context of replication. So replication is very important in science. So let's suppose I find a particular pattern in my lab. It will not gain widespread acceptance in the scientific community on that basis alone. Other labs have to find the same thing, including, preferably, some people who are kind of against me. Maybe they were kind of skeptical or critical of my idea, but they do the study with the same protocol that I used. If they find the same pattern too, then that increases our confidence that this is a real pattern, not found just through statistical fluke or something like that. This term is a big buzzword in psychology now because of something called the replication crisis. This was starting to happen around the time that I took my first psychology class, so my intro psych textbook did not include a discussion of this. So this has led to some really significant changes in how psychology is done. And I'll start with the punchline, actually. The punchline is that there was an attempt to get a bunch of studies from top psychology journals, follow their protocol exactly, and just see if you get the same effect. It depends on what your cutoff is for replicating the effect, but something like half of the results did not replicate. That's bad, obviously. You don't have to be a statistician to know that's not good. So, hence, replication crisis. So, following that, there have been a number of changes aimed at improving the replicability of our results. And to explain how those changes work, I have to talk about the p-value and statistical significance. These are difficult concepts. I'll say for whatever it's worth. They've done studies of psychology professors. Most of them misunderstand this concept. So, important to be careful here. So, let's say we're looking for a sex difference. So a difference between males and females in some behavior or psychological trait. Let's say we're looking for a difference in video game playing. Probably there is a difference, but let's say we wanted to look into it. So here's the population. The population is, let's say, Canadian males and Canadian females. We can't ask all of them, so we get a sample. Let's say the sample has 1,000 males and 1,000 females, randomly sampled from the population. And we asked them, how many hours of video games do you play per week? I don't know what it would be. Let's say the average for males is 10, and the average for females is 1. So here's something that's possible. It's possible that in the population, there's no difference. That in the population, it's whatever, 5 and 5. And just through sampling error, I happen to get more men in my sample who love video games. Even if your sampling method was perfectly random, that can happen just through kind of fluke. You happen to get more men who love video games. By the way, this is not on the key terms, but the term for the idea that for the hypothesis you want to reject is the null hypothesis. In this case, the null hypothesis is the hypothesis that males and females play the same amount of video games. So you're trying to find a difference. Null hypothesis would be there is no difference in the population. So before I get to the term p-value, just intuitively, it should look like it would be very unlikely that you would get a difference this big if this is true. It's possible, but unlikely. What that would correspond to is a low p-value. The p-value is the probability of getting your result if there's no difference in the population, or if the null hypothesis is true, same thing. So you want a small p-value. The smaller the p-value is, the less likely it is that you would get your result if there's no difference in the population. So I don't know what the p-value would be. You would actually need more information, but probably 0.00. It would be very low. Very unlikely that if you got 1,000 males and 1,000 females, you'd get a difference that big if there's no difference in the population. So before I add anything, does that make sense? Any questions about the p-value? So some of you might know there's a magic number that we want the p-value to be below. Does anyone know what it is? 0.05. So 0.05. Now, as I sometimes say to my class, it's not as though God spoke to us and said, thou must use 0.05. This is just a convention. It's used in medicine and psychology and the other social sciences. What this means is we want it to be less than 5% likely that we would get this result if there's no difference in the population. So that's the background. That's how the p-value is used. I should say, this is where the term statistical significance comes in. Statistically significant just means the p-value is below the cutoff that you set. Typically that's 0.05. That's all it means. P-value less than your cutoff. So here's the thing. So journals typically will not publish your results if the p-value is not less than 0.05. What this led to was a perverse incentive structure in science. Because sometimes you get a result of p equals 0.07, and you might think, well, there's probably something going on here. And what scientists would often do is play with different researcher degrees of freedom. And I don't think this was in the main malicious or ill-intentioned, but when you analyze your data, you have a number of choices. And there's not always a clear right or wrong answer. So one example is who to exclude from the data set. And you almost always have to exclude some people. So in my studies, when I was working at the University of Alberta, when we would do surveys, we would typically, as a matter of convention, exclude people who took less than 5 minutes to do the survey or more than 2 hours. If it's more than 2 hours, you're probably clicking in and out. If it's under 5 minutes, you're just randomly clicking. But you might find, p of 0.07 and think, well, I don't know, those guys who took less than 10 minutes, they're rushing quite a bit too. Maybe we exclude them too. And then, p of 0.04. We'll go with that. Other simpler things like, which dependent measure to use. Sometimes you measure more than one. If there's 3 of them and one of them has a p of 0.04, that's the one you publish. Now, the problem with this is if you keep trying these different things with your data, these kinds of exploratory analyses, eventually your likelihood of finding something with a p of 0.05 goes up, even if it's not a real effect. So what this fills the literature with then is false positives, is results that were obtained through basically statistical fluke, results that are not reflective of real patterns. There's a related issue, I didn't mention this to my 1200 class, but a related issue is publication bias, where the people who find studies of 0.5, 0.1, whatever, don't get published. Only the ones that happen to get below 0.05 get published. So probably some combination of those things led to the replication crisis, where the results that are in the journals often are not replicable. So the big, actually I'll leave this up, I'll just add this. The big buzzword now in psychology is pre-registration. So what this means is, there's different websites that allow you to do this. You say in advance in a public forum, this is what my hypothesis is, these are the measures I'm using, this is how I'm going to test my hypothesis, and these are the kinds of people I'm going to exclude. So you sort of tie your own hands behind your back before doing the analysis, and then you have to follow those steps. And the good websites that allow you to do this make it so that you can't change it once you publish it. So once you do that, to be clear, you can still do exploratory analyses afterwards, but then you have to be clear, look, I wasn't originally predicting this, I was just trying out some different analyses after the fact, so take this with more of a grain of salt. So nowadays, the good journals in psychology often will require this. They'll require that you've pre-registered in order to get it published. Any questions about these terms? Okay, another issue in psychology that's receiving more attention now, although this one is more expensive to address adequately, is the weird problem. WEIRD is an acronym. It's not meant to be a value judgment. It just makes it easier to remember. WEIRD stands for Western, Educated, Industrialized, Rich Democracies. So actually, it's a guy at UBC, Joe Heinrich, who originally pointed this out. Most studies in psychology are done with WEIRD samples. So places like Western Europe, Canada, United States, Australia, places like that. And as I said to my 1200 class, it's actually worse than that, because most studies are done with university psychology undergraduates from weird countries. I forget if I've said this to you, but psychologists are cheap. We don't like paying people if we don't have to. So as you all know, in this class, and this is standard in intro psych classes, there are potential opportunities to participate in studies to get course credit. That's a very common way of getting big samples for studies. But some people didn't require a lot of intelligence to point out, psychology undergraduates from weird countries are not a representative sample of the human species. And psychology, in theory, is supposed to be the science of the human mind, not the science of, psychology undergraduates from the United States. So there's now a renewed emphasis not only on replication, but cross-cultural replication. And there are a number of examples of patterns that were well established, but then someone tried to find the same pattern in China or India or sub-Saharan Africa, and then you don't find the same pattern. And this affects more things than you might think. I'll give you a pretty crazy example. Because you might be thinking, yeah, for moral beliefs or values, culture would be really important. But even for something like visual perception, there are interesting effects. So this is an example of the Muller-Lyer illusion. So have a look at A and B, and ignore the lines pointing out. Focus on the line segment in the middle. Which one appears longer, A or B? So show of hands, who thinks A appears longer? Who thinks B appears longer? So that's pretty standard. So this is, as I say, the Muller-Lyer illusion. This illusion typically is not found, certainly not to the same degree, in non-industrialized societies. Societies that are, not developed, like closer to being hunter-gatherers. That might sound strange to you, but here's why, probably, the Muller-Lyer illusion exists. If you live in a developed country, you're used to seeing things like this. And in this case, where the line is close to you, in the second case, it's further away. And so your brain gets used to assuming that this line is longer than it appears. So something that's farther away is larger than it appears. So you get used to that, but if you grow up in a non-industrialized society, there are not a lot of right angles in nature. So you don't get used to drawing that visual inference. So cross-cultural replication is very important. It shows up in places you might not expect. Okay. Next, we have to talk about two different types of errors. So, when making a decision about your hypothesis, there are two kinds of errors you can make. And to map them out, I'll distinguish between the state of the world. So, there's a fact of the matter about whether your hypothesis is right or not. So let's just use the antidepressant example. So I've made a new antidepressant and I want to figure out whether it works or not. This would be like from God's point of view or something like that. Does the drug work or not? So the check mark would be the drug works, X would be the drug doesn't work. And then there's my decision. So what conclusion do I draw based on the study that I performed? So I can either conclude drug doesn't work or the drug works. So if we're in this quadrant where I conclude the drug works and it in fact does work, no problem. I made the correct decision. Same here, right? No issue. Let's suppose that in fact the drug doesn't work, but I conclude that it does. This is a false positive or a type 1 error. So the falseness has to do with my decision. It doesn't make sense to say the world is false. That sentence doesn't mean anything. So positive means I concluded the drug works, but I made a mistake. It doesn't work. So as I said, this is also called a type 1 error. The other one, probably guess, called a type 2 error or a false negative. And by the way, if you want to remember which is which, the trick I used in undergrad is imagining that one of the lines rotated into a minus, so it's -1. That's what I use, but you can use whatever trick you want. So a type 2 error, or a false negative, is one where you conclude the drug doesn't work, but in fact it does. This can happen for various reasons. Any questions on this? Okay, there's then a section on critical thinking. I'm not going to spend too much time on this, so just a few things I wanted to highlight. One really nice phrase that the book talks about is the different attitudes we take towards evidence or towards a position when we want to believe it or when we don't want to believe it. When we want to believe something, the question we ask ourselves is, can I believe it? Can I find some evidence that supports this thing I want to believe? And the answer is typically yes. It's almost always yes. You can almost always find some evidence that supports a claim, if you look carefully enough. When we don't want to believe something, the question we ask is, must I believe Is the evidence so strong that I'm literally compelled to believe it? And the answer there is almost always no. Especially in an area like psychology, the evidence is almost never so compelling that you literally have to believe something. So the solution, the way to think, is to critically evaluate everything, even evidence that supports something you want to believe. The way that the bias I talked about plays itself out is if you look at two pieces of evidence and one supports what you want to believe and one goes against it, the evidence that supports what you want to believe, you'll take at face value. You won't look too closely. Oh, yeah, that looks good. No further analysis needed. If it goes against what you believe, you read it very carefully, trying to find problems. And almost always you can find some problems. No study is perfect. So what we should be doing is critically and skeptically evaluate everything. This relates to the term in the book, skepticism, which is about doubt, right? This is very important to the scientific mindset. We don't trust things as a matter of tradition or faith. We are skeptical. The Royal Society in the UK, one of the first scientific societies in the world, had a mantra, nullius in verba, which means take no one's word for it. Take no one's word for it. That's really important to a scientific way of thinking. Okay, once again, we'll finish early, probably earlier than last time. We have one section left. Try not to be too sad about this. So the last section is on research ethics. So a few things to talk about and then a short video as well. So psychology now requires that whenever you do a study with human subjects, you have to submit it to the ethics board. This emerged because of a number of studies that were ethically problematic. Many of them became famous. How many of you have heard of the Stanford prison experiment? Maybe 40%. How many of you have heard of the Milgram electrocution or obedience study? A handful have heard of that. Those are probably the two most famous ones. So actually, I'll show the video now. So I have some footage from both of those studies. So the Stanford prison experiment involved rigging a basement in a building in Stanford to be a prison and randomly assigning subjects to either be guards or prisoners. And that didn't go so well. So, and then the Milgram studies also. There's also some footage of that. Okay, so may not have been clear from that footage, but when it says that 2/3 of participants were willing to induce a potentially lethal shock. So you see how at the end he presses it and it goes silent. What they were then told is if they give no answer, that means it's incorrect. And 2/3 of people continued to administer shocks even after the learner appeared to be unconscious, just because a guy in a white lab coat was telling them. As another aside, so these are the two most famous cases. Leaving aside the ethics, which I'll talk about in a second, as a matter of scientific inference and scientific, replicability, the Milgram study, the electrocution one, was very well done. He did several replications, did it very carefully. The prison one, myself and many other psychologists regarded as basically a fraud. Because what he presented to the public was, this shows that when you have a certain role, like prison guard and the glasses, like he says in the video, that makes you behave cruelly towards others. But in fact, Zimbardo basically told them to be jerks. His mistake was leaving a long paper trail, and that's quite clear. And attempts to replicate the results without telling the guards to be jerks didn't replicate. So as far as scientific practice, leaving ethics aside, Zimbardo's was bad on multiple counts, yes.
Were they allowed to opt out of the experiment, the prisoners?
See, that's one interesting thing about it. it's sort of unclear. At the beginning, they are told you can leave, but then as the experiment progressed, if someone says, I want to get out of here, it's like, what do you mean? This is a prison. So that's one big problem, and so one of the ethical requirements now, if you submit to an ethics board, is you have to absolutely be allowed to leave at any time. Now, in the case of the prison study, they actually ended it early. After a week, it was just too much, so they called it off early. So anyways, as a result of these studies, it became a requirement that you submit your plan for an experiment before doing it to an ethics board, even if it's something simple like a survey. Any kind of study involving human subjects has to be approved before. I'll just say as an aside, when I did this kind of work, the ethics boards drove me crazy. I think people need to feel that their jobs are important, so they wasted a lot of my time with dumb stuff. Just as an example, one time I was putting out posters for the experiment, and I had the lab email, and they said, no, that's not okay. You have to have a person's email as well. And I thought, well, thank God we have you guys. What would we do without you? That's a really, anyways, but leaving that kind of thing aside, obviously it is good that they exist given some of these past abuses. Here are some things you have to do. You have to obtain informed consent before the study begins. So if any of you do a study here at Douglas College with, say, the honors students for extra credit, there will be a consent form at the beginning of the survey that you have to read and click agree. But even if you do that, to answer this person's question, or something related, you have to be able to leave at any time. There should also be protection from harm. So this includes physical and psychological harm. You can include things that could potentially make people uncomfortable, but number one, you have to include that in the informed consent. So in the consent form. So for example, as I mentioned, my studies often involved moral dilemmas, and reading them could potentially make someone uncomfortable or distressed. So I have to mention in the consent form that there are some dilemmas that involve death that may make you uncomfortable. And the degree of harm or discomfort should not exceed the amount that someone would typically be exposed to in a day-to-day basis. So reading some moral dilemmas, you might hear that in a philosophy class, that's not so unusual. Being locked in a basement of a university, depending on your friend group, probably not typical. So that would not pass today. You are allowed to engage in some deception. So in my own work, I also did some experiments on confirmation bias, but I didn't want people thinking that the studies were about confirmation bias, so I sort of led them on to believe that it was about memory. Because I don't want people thinking, ooh, how biased am I being? I thought that might mess up the results, so that's something that's actually quite commonly done. If that's done, you have to talk about it in the debriefing form. So the debriefing form is something you're required to give at the end of the study, where you talk about what your hypothesis was, why you included the measures you did, etc. And you also must address any deception that you engaged in. Hey, we kind of lied to you, sorry about that, here's what the study was really about. So that's ethics for human research. As I already mentioned when we talked about case studies, the rules are a lot more lax with animal research. This is controversial, so the book mentions Peter Singer, who's a philosopher I've read, I quite like him. He has argued that these requirements should be more stringent, but we won't get into that in any detail, this is not an ethics class. So the constraints that do exist, just to give some examples, you do have to minimize harm to the extent possible. So even if you're doing something like destroying a part of the animal's brain, if anesthesia is available, you use that, you reduce harm as much as possible. And the research should serve a clear scientific purpose. Now, crucially, it doesn't have to serve a practical or medical purpose. You can do research that involves harming animals, even if it's just to find out what the nucleus accumbens does or something like that. Okay, and then the last section, which I have very little to say about, is respecting truth. Don't do things like fake your data. Should be simple, but some people still can't manage to figure it out. There was a recent famous case in the United States, Francesca Gino, and this is almost too good to be true, but Harvard did a long investigation of her. Hopefully this video doesn't go viral because she sued Harvard for firing her, but the documentary is pretty clear. The punchline is she faked her data in a study about dishonesty. So you can't make that, well, she made it up, but the story is so funny you can't make it up. Okay, any questions about chapter 2? Okay, don't be too sad, but class is over. I'll stick around if you have questions. The test review tomorrow, and if you don't come to that, see you next week for the test. Yep.
Did you say you were going to talk about the written question?
Very good. This is your new favorite classmate. That I forgot this morning too, actually. So I'm still a little under the weather. My brain is not fully recovered. Okay, so the written question. I should ask for you to guess. I did kind of say like this is the most important thing in the course. So here's what the question will look like. I will describe a positive correlation. I'll just say, suppose that it's discovered that these two variables are positively correlated. Why does that not imply that A causes B? You know, the first variable causes the second variable. And then I will ask you to describe how you would conduct an experiment to test whether A causes B. So that's the written. Any questions about what that would look like?
Is that the same one for 1200?
Yes, the same as 1200.
And you're going to post that, right?
I'm going to post what?
The review, sorry?
Oh, like the review like
Yeah.
tomorrow? Yeah, so the review tomorrow, if you can't make it, I will film that and post it as well. And yeah, for my 1200 class, this is such an important question, I'm asking you in both. Okay, have a good night.